Hi, it's Chris here from the EQ Mod project. In this tutorial we're going to look at a few more things to do with alignment, particularly the proximity range and the point filter. The proximity range slider is used to prevent points being added to your model that are very close together, and this helps keep points within your model evenly distributed. The reason why this is a good thing is that if points are close together and you're using a 3-point type transformation, then the triangle angles can become rather acute, and this can lead to some inaccuracies. By setting the slider, and I normally have mine wound right up to 15 degrees, I think by default it's off, but I normally wind mine right up. What happens is that when you add a new point, a search is made through all the existing points to find and remove any that are within, in this case, 15 degrees of the new point. The new point is always added to the model because we assume that new data is always good data, but older points that are effectively redundant are removed, and in this way we can obtain a nice even distribution of points. And there's also a performance benefit in that you're not making your model enormously large. Obviously the larger the model, the much more time it takes EQASCOM to process it. Okay, moving on to the point filter. I just need to rearrange things so we can see everything we need to see. Okay, as you can see, I've already loaded up a 16-point model, and we have a 3-point transformation currently being applied, as indicated by the red triangle. You can see that the triangle is formed by 2 points on one side of the meridian and 1 point on the other side. Now, it can be the case that the pointing corrections themselves are characterized by sky position, so points on one side of the meridian may well apply a different type of correction than those on the other side, and the same can be true of points within quadrants, particularly if you use a telescope that exhibits some mirror flop. Now, the point filter works by restricting the points that are available to provide the correction. With the setting on all, there's no restriction, and all these points are considered. The way EQASCOM works is it basically works out all the permutations of all the triangles that can be made using these points, and finds the triangle that has a center point closest to where the mount is, or where the mount wants to go, and those are the 3 points it will use. If I change this to pier side, you'll see immediately the triangle changes. The points being used for the transformation have changed. And this is because only the points on this side of the green line, the meridian, are now being used, or now being considered as part of the correcting algorithm. If I change to a local quadrant, then it will change again, and now only these 1, 2, 3, 4, 5, 6 points are being considered, and so we get a different triangle again. I tend to use local quadrant on my observatory set up. But obviously, to do this, you need to have at least 3 points in each quadrant of the sky, and probably, as I have, 4, maybe 5 different points in each quadrant. Okay, now there's one last thing I'd like to show you, and to do that I've got to move the mount position. So I'm using a bookmark go-to that I've previously set up. Hopefully this will go to the right place. As you can see, as the mount moves across the sky, various different triangles come into play, or nearest stars. Right. Okay, that's what I wanted to show. Now, you might think that what you're seeing here doesn't really look right. The nearest point is shown with the yellow circle. And looking at this representation of the sky, clearly you'd say that this point here, this point here, and this point here are surely closer to the mount than this one right out here. Looks strange. The explanation for this is that when we talk about nearest point, we mean nearest in terms of angular movement of the mount, of the RA and deck axis. Although the other points look nearer, this is because we're near the pole. And for instance, to get to this point here, the one that appears closest, would require a significant amount of right ascension movement to rotate around the pole and then move in. Whereas moving to the point that is shown as the nearest point actually requires a much smaller amount of smaller angular movement of declination. Something you perhaps have to spend a little while getting your head around, but it's an effect that we're showing a two-dimensional representation of the sky here, and the fact that the way the mount moves in right ascension is around the pole, and so generally moving anywhere near the pole, you're going to see this kind of effect. It looks odd. Trust me, it's showing the right information. Okay, that concludes this tutorial. Thank you.